So here's a question. What's the integral 0 to 2 pi sine of t dt? And remember here in chapter 5.2, we're still taking a geometric kind of point of view, an area under curve kind of point of view. If you've taken a calc class before and kind of remember some stuff about antiderivatives, which we already saw in chapter 5.1, you can do it that way, but let's really see what's going on with the geometry here. So anytime you have an integral, it's usually good to plot it. So we'll plot sine of t from 0 to 2 pi, and it looks like this. Pretend that's perfectly symmetric, right? What is the net area under the curve there? So we're saying take the area under this part of the curve and the area under that part of the curve. Well, this part has a negative area and that part has a positive area, and it's perfectly symmetric. So the net area is 0 because the lower bump exactly cancels the upper bump. So maybe that seemed a little too easy. Should we do something harder? How about the integral from 0 to pi sine of t dt? Again, it's good to draw it. This time it's just that first bump. Well, here in chapter 5.1, we want to kind of do geometry. This kind of looks like a semicircle, but it's not a semicircle. So let's write that. One way we can tell, sine has a derivative of 1 or 1 here and -1 here, so it's slanted as it's coming toward the start, from the start point and at the stop point, whereas semicircle has a perfectly vertical tangent line at the start and stop. So that's one way to tell. Also, this tops out at 1, so it would have, if it was a semicircle, it would be trying to have a radius of 1 vertically and pi over 2 horizontally, also not sounding like a semicircle. So it turns out here in chapter 5.2, we can't get an exact answer for this. But what can we do? We could try guessing, right? Or lower bounding and stuff. So what's a quick lower bound? It would be all 0. What's an upper bound? It would be, well, the maximum height is 1. So the height of 1 times a width of pi minus 0. How about a guess would be halfway in between those two. So our guess would be basically 1/2 times pi minus 0. And it turns out that's pretty close. Do you think it's exact? Well, think about what area we're including here, what area we're not including. Then let's go on and do a more interesting one. How about the integral 0 to 2 pi of 5 plus sine t dt? What's the first thing we do? Draw a graph. So here's 0, here's 2 pi. This is a sine wave that has been shifted up by 5. So it'll start here at 5, it'll go up to 6 around there, and it'll come down to 4 around there. And that worked. So here's pi. What can we do to talk about the area of this? I wonder. Maybe upper bound, lower bound, and guess. Now this time the lower bound is slightly more interesting. This function never gets below 4. So our lower bound is a height of 4 times 2 pi minus 0. What's our upper bound? It's a height of 6 times 2 pi minus 0. And then what's our guess? Halfway between 4 and 6. Pretend that all worked out. Here, we know that this should be exactly touching 5 by the time we get there. So our guess would be 5 times 2 pi minus 0. And what do you think of that guess? Do you think that guess is perfectly accurate, or a little too high, a little too low? All right. So let's see this in chapter 5.1 and 5.2 terms. In chapter 5.1, indefinite integrals, we would have said the integral of 5 plus sine t dt equals the integral of 5 dt plus the integral of sine t dt. So the integral of a sum is the sum of the integrals in chapter 5.1. Here in chapter 5.2, we're saying the integral from 0 to 2 pi, 5 plus sine of t dt, is equal to the integral 0 to 2 pi. Well, can we say that this area is the area of a box of height 5 plus the area under the curve of a plain old sine wave? That's kind of what we're guessing, right? So 5 dt plus the integral 0 to 2 pi sine of t dt. So we're saying that first area is a box of height 5, 0 to 2 pi, and the second area, we've got the sine wave going on as before. And what did we say about the integral of a sine wave? Well, this area exactly cancels that area. So this area was 5 times 2 pi minus 0, and this area is 0. So we get a total area of 5 times 2 pi minus 0, which was exactly our guess. We are excellent guessers. So altogether, what we're seeing here is that you can split a definite integral into the sum of the definite integrals of the individual parts of the function. So you can split a definite integral of a sum into the sum of the definite integral parts. And where do those definite integral parts start and stop? Because definite integrals have to start and stop somewhere. They both start and stop at the same place as the definite integral that we started with, rather than going like a to c and c to b. So here, it looks like we're splitting an integral horizontally because we're writing it and it takes longer to write it. But really what we're doing is splitting the integral vertically into the vertical sum of this constant, it doesn't have to be a constant, plus this function, which is not constant. So this is more of a vertical split of an integral. The starting at a going to c, starting at c going to b, that was a horizontal split of the integral.